Hey guys, I hope you're doing well. This tutorial will be part 2 of my hexagon tutorial series. If you haven't followed along with part 1, go do that now. In this video, we'll build the shader needed to outline an arbitrary amount of hexes. The project will be available for you to download for free on my GitHub. A link to my GitHub repo will be in the description down below. Before we dive in, remember to comment, like, subscribe, and ring the notification bell to be notified of when new tutorials go live. The first thing I want to do is change the hex colors so we can clearly see where one hex ends and the other begins while they're all at the same height. So for now, I'll just randomize the color between black and white for each hexagon. So open up the hex spawner script from the last tutorial. I'll write a quick method that takes a mesh renderer as a parameter. First, randomize a value between 0 and 1 to be our shade between black and white. Create a new material instance that is a copy of the shared material. We don't want every hex to be the same color. Set the base color of this new material to be our randomized shade. Then assign the material instance to the mesh renderer. Finally, call the method and pass in the mesh renderer from the new hex. Respawn the hexes. Awesome, looks great. Time to create the shader. Create a new PBR shader graph and open it up. I'm going to change the preview to our hex mesh so we can see what's happening. To highlight the edge, we must first know where the edge is. The origin of our hexagon is the center of the bottom face. So the center of the top face is the up vector times the height of the hexagon. This works because our hexagon is exactly 1 unit tall, so multiplying by 0.5 makes it half height, and by 2 makes it double height. We can find a point along our edge by simply multiplying the direction to the edge by the apothem that we calculated before. So let's execute this in shader graph. First, we need to calculate our apothem, so add a radius exposed property. Remember our formula from last video and recreate it in shader graph. The square root of the radius squared minus 1/2 the radius squared. Then turn it into a subgraph to keep it clean. Be sure to name and hook up your output values. So let's create a subgraph to calculate our edge. It's going to output a 1 for all points along the edge and a 0 for everything else. Add our inputs as properties. Up, default to 0, 1, 0. Direction to edge, default to 0, 0, 1. Height, default to 1. Apothem, well, a rough estimation of 0.85 is fine here for visualizing. We'll feed it in later. And thickness, default to 0.1. So the height times the up vector plus the apothem times the direction vector will give us the point at the middle of that edge. Now we don't much care exactly where that point is, but more where any given point on the hex is in relation to it. So take the object position minus that point on the edge. Let's look at some math. The world up vector cross the direction to the point on edge gives us L. L normalized is Ln. Because vectors don't care where they are in space, the vector that points left from P, our point on edge, is the same vector as Ln. If I is any given position on the hex, then I minus P gives us some vector A. This is what we just did in shader graph. If we project A on Ln, we get A1. You can see here that both of these A1 vectors are equal. But that's not quite what we want, as we need the distance to the edge. So A minus A1 gives us the vector A2. This is called rejection. You can see here that both of these A2 vectors are equal. Now we know that the magnitude of A2 is the distance to the edge. To calculate the magnitude, we would take A2 dot A2 and square root it, because any vector dot itself gives us the magnitude squared of that vector. Because it's cheaper to square something than to square root something, we can instead square our thickness before comparing it to the magnitude of A2 squared. So if thickness squared is greater than the magnitude of A2 squared, then we know that the point is on the edge. Essentially, we're calculating a cylinder whose radius is thickness and it lies along the edge. And then we're checking to see if we're within that cylinder. Back to shader graph. First, we need to take up cross direction normalized. This is ln. Then reject a that we calculated before from ln. And take the dot product of itself and square the thickness. Let's compare the two values branchlessly. Subtract the two, take the sign, which is either a -1 when the value is negative, a 0 when they're equal, or a 1 when they are positive. We only care about when they're positive, so take the max of that and 0 to turn any negative ones into zeros. Output that to our output node, and there we go. You can see the cylinder drawn at the edge. This branchless greater than is actually really helpful, so I'm going to turn it into a subgraph as well, and go ahead and clean up those nodes. Now we have a subgraph of the edge, but we don't want to display these side arcs, so let's take the normals into account. We don't want to cancel out the up normal or the direction to the edge, just the side faces, so let's start with up. In our main graph, add two new exposed properties, a vector 3 up defaulted to 0, 1, 0, and a vector 1 epsilon. This is how much wiggle room we will allow. So this should be a really low value, like 0.001. Also, create a normal vector node, set to object mode. This is the normal of any given point on the object. First, take the dot product of the normal vector and up. Then feed the epsilon node into a 1-. Then go ahead and reuse the greater than subgraph that we created a moment ago. So if the dot product is greater than the wiggle room, we paint in with a 1, else a 0. Plug it into the albedo. Awesome. Since this graph will tell us if any point is facing any normal, turn it into a subgraph. Name the vector 3 parameter normal, save it as is normal facing, clean up the graph, and reconnect our properties. Now that we know the up face, let's find the forward face. Create a vector 3 node, enter 0, 0, 1. Reuse the is normal facing node that we just created, but this time with the forward vector. Plug that into the albedo channel to see the edge face highlighted. Now we want to simply OR gate these. A branchless OR gate for two values that are either 1 or 0 is simple. Start by adding them together. This will either be a 0 if both are 0, a 1 if either is a 1 and the other is a 0, and a 2 if both are 1. Since both being 1 is fine, simply take the minimum of that and 1. Turn this into a subgraph called OR gate. Name your properties A and B, and then clean up the graph. Now if we multiply this by our edge, then each of the arcs get multiplied by 0 to cancel out, leaving only our edge highlighted. So add in our edge subgraph. This is a good time to connect up, direction to edge, and apothem, and add the properties the edge subgraph needs. The height and thickness are both vector 1s. Height is defaulted to 1, while thickness is defaulted to 0.1. Now that we have one edge finished, we need to highlight the other 5 edges. We can do this with some clever subgraphs. Let's turn this into a subgraph, excluding the apothem, the up face, and the vector 3 forward direction. Clean up, name the direction to edge, apothem, and is facing up 1 or 0 properties. Name your output is on edge marking. Now, because hexagons are mirrored, we can calculate the opposite edges really easily. Add a new output is on opposite edge marking, copy paste everything except for the direction to edge, feed the direction to edge through a negate node, then into the edge subgraph and the is normal facing node, and feed it into the new output, then save. Back in the main graph, add the two outputs together and feed it into the albedo channel to see the two edges highlighted. Now that we have one set of edges, let's do the diagonals. Just copy and paste this group of edges 2 times. Look up the apothem and is up facing to the respective slots, and delete the direction to edge. Add all the results together and feed it into the albedo channel. Let's calculate the direction to 1 and 4 first. Make a new vector 3 node, feed the apothem into the x-axis, and the radius times 0.5 into the z-axis. Then normalize it. The last one is easy. Do the same thing, but use negative 0.5. Because we're adding these together, the points are adding up to be more than 1, so just saturate it. Now that we've highlighted all the edges, let's add an easy way to turn them on and off. Add 6 exposed bool properties, 1 for each edge, 0 through 5. Be sure to set the reference fields. Let's start with 0 and 3. Add the branch node. Feed the edge 0 bool into the predicate slot, and is on edge marking, which is a 0 or a 1, to the true node. Leave the false slot at 0, and then do the same for edge 3, and then replace the add connections. Do the same thing for edges 1, 2, 4, and 5. Awesome. Now we can toggle each edge on and off. Since we've randomized the color of our hexagons, let's add that functionality in. Add 2 new exposed color properties, base color and edge color. Multiply the output of the saturate node with the edge color, and take the 1 minus with the saturate. Multiply it with the base color. Add the two together and output to albedo. And the shader portion of this is done. Now we just have to write a little bit of code to turn on the proper sides. Before we get to the code, let's add the shader to each hex. On our hex material, change the shader dropdown to hex outline. Change the edge color, and press spawn hexes. Dope. We want to toggle the outline around a hex when we click on it. So to make our lives easy, let's use the new Unity input system for this. You can add it in the package manager. Doing so will restart your editor. Now let's add a select hexes mono behavior. Since we're detecting where the player clicked, we need the camera to form a ray. Then write a public left-click method that takes callback context from the new input system. If callback context is anything other than performed, return. Our raycast takes in a screen point to ray from the camera at the mouse position, and an out raycast hit. If for some reason the hit collider is null, just return out. Get the hex component on the hit collider and call toggle select on it. Let's define the hex mono behavior. It has a toggle select method, as we just used. If some bool selected is true, call deselect, else call select. For now, select just sets selected to true, and deselect sets it to false. The selected property should be visible by other classes, but only changeable within this class. Now is a good time to update our hex spawner script to use this new hex type. Change the prefab, update the list, change the instantiate, and destroy the dot game objects instead. You may have to reserialize the list in the inspector later, so remove the read-only attribute if you had it like I did. Respawn the hexes so they all have the new hex script. Add the select hexes and player input components to the hex spawner object. Create the input actions. I'm just going to bind the left mouse button for now. Assign it to the player input component, and send a Unity event to call the left-click method on the select hexes component. Since the values we want to change are on the material, we need a reference to the mesh renderer. Let's start with the deselect method. Unity shader bools are just special floats, so loop 0 to less than 6 and use renderer.material.setFloat to set each edge bool to 0. A consistent naming scheme for your reference fields in the shader makes this really easy. To make our lives easier for the rest of this tutorial, I'm going to create an enum hex neighbor direction for each potential neighbor a hex can have. It's important that this enum is in the same order as our edge numbers, so 0 is up, 1 is up right, 2 is down right, all the way until 5. We want to be able to loop over this enum easily, so make a new script called enum array. This is a static generic class where tenum is some struct enum. Create a private static read-only tenum array called _values, and another values that is not read-only that returns _values. Then add a static constructor that sets _values by getting the values of the enum type, which is a low-level array type. So cast that with link to an IE numerable of type enum, then again use link to convert it to an array. Back to the hex script. We're going to need a reference to the hex spawner, so let's just find that in Awake and cache it. We are also going to need to know what index this hex is, so I'm going to create a custom serializable struct with row and column for this, but a vector2 would work as well. If we want to be able to view this index in the inspector, we must convert our hex script into a serialized mono behavior from Odin inspector and add the Odin serialize and read-only attributes to it. Then write an assign index method that takes in an index and sets the hex index property. Then in the hex spawner script, call this assign index method on the new hex and pass in a new index. Create a method neighbors with direction that returns an IE numerable of a tuple that contains the hex neighbor and the direction. Time to loop the direction enum. For each direction in enum array of type hex neighbor direction dot values. Get the neighbor at this hex index in the current direction from the hex spawner, then yield return a tuple containing the neighbor and the direction. In the hex spawner script, let's fill out the get neighbor at method. First, we need the offsets on the row and column from our current index. Write a get offset in direction method that switches on the direction and returns the proper offset tuple. Because of how we generated our hexes, if the row is even, we may need to use a different column offset, so pass that bool in. This switch is a bit much, so take your time and copy it carefully. Then return the hex at that hex index plus the offset if that hex is in bounds, else return a null. To check if a hex is in bounds, let's write a simple method on the Hex Grid struct that takes in a row and a column and returns true if both the row and column are in bounds. We can do this mathematically by adding two properties, max row and max column. Back in the hex script, let's write the select method. Loop over every tuple returned by neighbors with direction. If the neighbor is null, meaning we're on the edge of the grid, or if the neighbor is not selected, we want to turn the edge in that direction on. I write an update edge method that toggles the edge in that direction passed in. We want to pass in either a 0 or a 1 for the value parameter. So get the existing float, subtract 1, take the absolute value of that, then floor it to an integer. I use an extension method for .floor, but you could just wrap it in a mathf.floor to int, similar to the absolute value. So if it was a 0, we get a 1. If it was a 1, we get a 0. Now we might need to toggle the neighbor hex's edge as well. So let's write an update neighbors method and call it at the end of both select and deselect. Loop over every tuple returned by neighbors with direction. If the neighbor is not null and it is selected, then call update edge and pass in the opposite direction. I extend the hex neighbor direction enum with a .opposite method. Cast the direction to an int, add 3, then mod 6. Then cast it back to a hex neighbor direction and return it. Back into Unity, serialize the mesh renderer on the hex prefab, save it, and update the material so all of the edges are off by default. Then respawn the hexes. Adjust the camera so it's looking down at the grid. Remember to add a convex mesh collider and a kinematic rigid body to the hex prefab, and respawn them again. Then press play and start clicking on hexes. Pretty cool, right? There are so many things that we can do with this. Be sure you share pictures or videos of any cool things that you make with this technique. Special thanks to my patrons on Patreon. You three really make content like this possible. Thank you from the bottom of my heart. I mean it. You guys are awesome. If you'd like to support my content and see more videos like this, please consider supporting me on Patreon. Stop by my live stream on Twitch, Wednesday through Saturday, 1 p.m. to 7 p.m. Pacific. If you enjoyed this tutorial, comment, like, and subscribe for more. Stop by my Discord server. We have hundreds of awesome people making awesome things. Check out my assets on the Unity Asset Store. Try my games and demos on my itch.io. Thanks for watching.